Hello and welcome to another video where I'm going to talk about C++ as usual. Today's video is another blog myth-busting, performance myth-busting video like the previous one. So today's blog is from Mohammad Nasirifar, and what it goes through is multiple ways of calculating some kind of algorithm in compile time, at compile time. There is the C++98 version, but the algorithm that it is trying uh, to figure out is to calculate is figuring out the prime numbers. What algorithm we use it is called seeds of Eratosthenes. I have no idea how to actually pronounce that. There's a wiki link here. What the algorithm does is it iterates through the numbers, chooses one number, and then crosses out all the uh, divisible numbers to that first selected number. So it selects 2, crosses out divisibles, selects 3, crosses out divisibles, 5, 7, 9, and then whatever is left are the prime numbers because they were not divisible by any other numbers. So yeah, that is what the algorithm does. You can see the wiki link in the blog post. It is some simple algorithm. And then we have C++98 versions, that is template metaprogramming, C++14 version, that is still template metaprogramming. And then there's C++17 that has two versions. One is kind of template metaprogramming, and the other is using constexpr functions. And what it does is it is trying to uh, save the value of is prime for each number inside a boolean that is constexpr static to a type, and then you can access that value like this. This is kind of template metaprogramming, and it uses constexpr as well. Then there's C++20 version that uses the consteval function that returns the whole array, and what it does is use that array instead of the type to store the calculated values. So the point that I take issue with this blog is that constable functions appear to be faster in this case as well. I have no idea the way that they've actually benchmarked this. In C example, a constable function generates cvary 2 times faster than a constexpr function. I still have no clue how they've actually managed to calculate this. There is no benchmarks provided in the blog, and I am also not sure if they're talking about runtime performance or compile time performance. Anyways, however, I'm not going to actually run any benchmarks here because, as you will see, we don't need to. So let's first of all, let's take a look at what these codes are doing. As you can see, they are doing different things completely. The C++17 is using some type to store the values, and C++20 is generating some kind of array and return it. There is no need to actually do this in C++17. And let's go to the compiler explorer of this code, and you can see that these are actually completely different algorithms. So this is the C++20 version, and we have the cvary here, and the first thing that comes to mind is that he has declared a sieve consteval, and sieve function here is promised to run at compile time. However, this copy here, this copy construction here that we are copying cvary is not guaranteed to actually run at compile time, and it is not run at compile time, as you can see. So I am actually unable to compile this at O3 because it sees the runtime limit on Compiler Explorer. So I'm going to reduce this number to 1000. Sorry, 100, 103 maybe. Okay, so now I'm trying to compile this here again, and let's see if it actually compiles. Yeah, and you can see that still on O3 we are copying the result of seed here to this stack array we have here. So this actually is not good for runtime. So what I would do is make this static constexpr. There's a C++ weekly video that explains why this static here is necessary. And then you can see that all our cVary is moved to some kind of data section or code text section in our binary. So there's actually no runtime stack or runtime copying of this array. The code has been removed. So here I will try to make this constexpr, and let's run this on C++17. And you will see that, yeah, the exact same code is generated. So if this is faster, this is actually still available in C++17. So what is the difference between constexpr and consteval here that comes to mind? So the difference is actually nothing special. Consteval is just telling that my function can only be used at compile time context. So you cannot pass I here, for example. Let's say I'm calling my consteval with 0. 0 is available at compile time, so it can be calculated. However, if I pass I, there's compilation error. I is not available at compile time, and as you will see, I have compilation error here. Then you have this constexpr version that both accepts runtime values and compile time values. Here I am forcing my constexpr function to actually run at compile time. If I do something like this, compiler is still can still run your code at runtime. So that you will have to do something like this to make sure that your function is actually run at compile time. That is the reason, excuse me, that is the reason why consteval is actually introduced to the language. So you don't have to write something like this. You can just make it consteval. However, it removes your ability to actually use your function at runtime context as well. Let's say this is a generic function that can be used both at compile time and runtime. I definitely want it to be constexpr, so I can use the same code for both runtime and compile time. So that's it for this video. This was a quick video on myth busting some blogs. I will probably do more myth busting videos later as I read more blogs. Thanks for watching. If you like this kind of content, make sure to like and subscribe. Thank you.